In the previous lecture, we discussed about the synchronization mechanisms that are available in NVM. So along with that, there are multiple other features that are supported by NVM. And in this lecture, we will try to go deeper into these different mechanisms or features that are available in the NVM module. So to summarize here, the different modules or the different features that are supported are the synchronization, CRC based comparison, error recovery mechanism, write protection, static block ID check, write verification, and setting of RAM block states, and finally the NVM configuration check. Let's start with the CRC based comparison now. So CRC based comparison. We came across CRC when we discussed the different kinds of blocks like a RAM block, ROM block, etc. So there it was an optional parameter and we are able to calculate and store the CRC there. So now we'll discuss what happens with this CRC. So this CRC based comparison, as I told you, is a configurable functionality. So we can configure and enable this functionality if required. The different generation routines that are supported are 8, 16, 32-bit. All these different algorithms are supported. Now how does this work? See, if the CRC check happens, okay, and if there is no error, then the write to RAM block is skipped. So if you're trying to read in the starting time using read all API, for example, so at that time, if we see that there is no CRC error, then we can actually skip the write to RAM block. So this way we can actually save the write cycle because we are effectively using the memory. I mean, if the CRC check gives no error, so we can actually save the write cycles. So this is about the CRC based comparison. It is just a check that will help us to compare the different data and skip if there is no CRC error. But just remember that there is still a chance of error. For example, if the bits change, but they change in such a fashion that the final checksum is still the same. So in this case, even if the CRC matches, we are still having the value is wrong. So we should be very careful when opting for this method because it's not 100% foolproof. It has this problem that this kind of scenario will face this issue. Now let's discuss error recovery. So in error recovery, we have three types of error recovery, of which the first one is implicit error recovery. So this implicit error recovery is used for native and redundant block management types. And to use this, we'll have to configure any of these parameters. One is NVM ROM block data address or NVM init block callback. So if we configure these callbacks or address, the data will be fetched from there. And this is called as the default data. So we can actually fetch the default data if this is configured. So this is called as implicit error recovery. So suppose any error happens, then we have this backup option to get this default data loaded. Next one is explicit error recovery. This is available for all block management types. We are able to retrieve the ROM data by calling the API nvm restore block defaults. So using this API, we will be able to retrieve the ROM data. So one special case here is that for the case of dataset, before calling this API, we need to ensure that the corresponding index must be also set. So we need to set the index first along with the calling of the API to effectively use it for the dataset management type. And finally, there are some other recovery mechanisms. For example, for NVM block redundant block management type, loading RAM block with default data is also possible. So this is one other recovery mechanism that is available. Let's look at the write protection feature of NVM. So if we configure a parameter that is NVM block write protection, this we set it as true, then we can actually prevent NV block modification. So if there is some value that we don't need to get modified, we can set this parameter for that block, and then this block modification can be prevented. Note that the RAM block can still be modified. We are protecting the NV block, not the RAM block. So just remember that there is one difference here. For NV block, we are giving write protection, but that doesn't mean RAM block is also protected. Next, let's check what is called as the static block ID check. Every time a NV block is updated, an ID named static block ID is also updated. So just remember, whenever the NV block is updated, we update something, an extra ID, which is called as the static block ID. And where it is updated, this value is stored in the block header. So the block header is used for storing this static block ID. Now this static block ID is compared against requested block ID to detect any errors. So if somebody is requesting to access this block, the static block ID is compared against the requested block to detect any error. So this is a feature that is provided by NVM to get checking for any errors. Now if error is returned after comparison, we will set the RAM block status to invalid unchanged. So there are some RAM block states that are available, of which we are using the invalid unchanged when the error is returned. We'll be looking at the RAM block states separately in another lecture, but just for now, just understand that we are setting the RAM block to invalid state because we have got an error. Next, we have write verification feature of NVM. In write verification, after writing to the NV block from RAM block, an immediate read can be performed on the NV block to check if it matches with the RAM block. So it's simple. Just after writing, we'll perform an immediate read operation. And then we'll check whatever we tried to write into that block, is it still the same that we are having with us? So this is called as write verification. We are verifying if the write is correctly done. Now if there's a mismatch, definitely this is an error case. So we'll have to perform write retries. Now read operation failure does not lead to read retries. Only the write operation failure will lead to this retries. Now let's check the RAM block handling using NVM set RAM block status API. All these APIs we'll be saying here will be discussed in detail in the upcoming slides. But for now, it's important that we just mention these so as to get an idea of how the NVM features are used. So this is just an API, NVM set RAM block status API. And it's used for RAM block handling. So let's divide this into two parts. One is the startup phase and the second is the shutdown phase. So during startup phase, there is one API which is called named NVM read all. So this API, I'll just give you an idea. We'll be discussing this API separately. But just for now, you understand that this is an API which is used to read multiple blocks at the same time. And this is done usually at the startup phase. So during startup phase, we are performing NVM read all operation. To prevent RAM block from being overwritten, we have to follow the following steps. To prevent the RAM block getting modified, we have to follow some steps. Let's look at what are the steps. The first one is that it has to be stored in a reset safe, no init RAM area. If you remember during memory mapping, we discussed about the different memory sections. So this is the no init RAM area we are speaking. So if this is the place we store the value, then it is in a reset safe place. So that means even if after the reset performed, we'll have some value that is still available. Another thing to ensure is that the CRC calculation shall be enabled. This feature should be enabled. And finally, NVM set RAM block status API needs to be enabled. To use this API, we have to actually enable it also from the configuration. And once that is done, only we can actually use this API. So once all these three steps are fulfilled, let's look at what happens. Now, when the RAM block data is changed, we will be able to call this NVM set RAM block status API for the RAM block, and then we can store the result variable in no init RAM area. So any change in RAM block, we'll be able to first set the RAM block status API, and then we will be able to store the result in a no init RAM area. Okay, so that even after a reset, we'll have this value preserved. So during net startup, NVM calculation of CRC of the RAM block will be calculated, and it will compare with the stored CRC value. If matches, data will not be overwritten. So if the data is matching, we will not overwrite the data. Otherwise, RAM block data is overwritten with the data from NV block. So if the CRC check during the net startup, we are getting a matching value, then we will not need to overwrite this value. But otherwise, we will have to take the backup from the NV block. So this is how we are using the RAM block handling using the NVM set RAM block status API during the startup phase. Okay, what are the initial conditions we need to check? The three conditions are the storage of this value in the reset safe area, enabling the CRC calculation, and finally enabling this API to be used. Then only we can effectively use this feature to set the value, the status of the RAM block, and then retrieve it during the next startup phase. Now, if this fails, we will load the default data if we have configured that. So if the overwriting with the data from NV block is failing, then we'll have to go for the last option, which is take the default data if it is configured. Now let's check the shutdown phase. So in shutdown, we have the NVM write all API that is used. Okay, again, we will be discussing NVM write all API separately. But for now, we will have to briefly discuss this API and how it is at this point of time, what are we doing. So during shutdown phase, we have to first check these conditions. For example, if NVM set RAM block status API is false, then NVM copies all blocks selected for NVM write all and writes to the NVM memory. So if this API is false, then NVM will copy all blocks which are selected for this write all operation, and then it will be returned to the NVM memory. Now, if suppose in configuration we have enabled this API, we can actually use this to save the write cycles. How can we save that? See, only those RAM blocks selected for NVM write all with the previous call of NVM set RAM block status, this API is called, and the argument passed is the block change set to true, and this will be considered for NVM write all. So suppose there are two use cases. So one is the case when this API is not available, and when one case is when it is available. So when the API is not enabled, the set RAM block status API is not available, then we have no option but to write all the blocks to NV memory during NVM writer. So this will not help in saving write cycle. Now second case is when the API is available and enabled. Once we call the NVM writer, just before that we will call the set RAM block status with parameter block change to true. So only those blocks for which this was called in this manner we will update using NVM writer. And this will help us to save the write cycles because only those blocks that got changed will now be returned to the NV memory during shutdown phase instead of writing all the blocks at the same time during shutdown. So this is how the RAM block handling is done using this API during shutdown. Now let's discuss something called as the NVM default blocks. So any configuration of NVM that you see in any project, you will have some reserved blocks. These NVRAM blocks are already reserved, and these are having IDs block ID 0 and block ID 1. So let's try to understand what are these for. The block ID 0 is not really used for any actual storage. So this is the first important concept. It's not used for any actual storage, but it is used to handle multi-block request triggered by NVM read all or NVM write all. So whenever any of this operation takes place, at that time it is using this block ID as the reference. That's all. So only these APIs need this block ID, and other than that, it is not occupying any real storage. That's all. But it's reserved, so you can't use this block ID for any other storage. Then comes the block ID 1. Okay, again this is reserved, and this is used to contain the value, actual value. And what is the value that is stored? This is the NVM configuration ID, or we can say NVM compiled config ID. So in this particular block, we'll be storing an ID that helps us to understand or locate what is the current configuration. So for each configuration, we'll give it an ID so that we can easily understand how is the configuration or what is the current configuration. So for example, if I make some changes in the current configuration, then I have to update this parameter, which is NVM compiled config ID. And this will be reflected in this block ID. So once this is done, we will be able to, for example, we are again restarting. So at that time, during NVM read all, from NVM, NV block itself will have this value stored. So we will be comparing this value with the current configuration ID and check if there is any mismatch. So if there is some mismatch, we can actually do some action, which we'll be discussing in the next slides. So this block ID 1 is of the type redundant, and it is also having the CRC enabled. So that's about the default blocks. Now let's try to understand how the configuration changes are handled. NVM dynamic configuration. So this is the first parameter that we will need to use with the configuration changes. So we have two parameters, and this is the first parameter that we need to know when we are dealing with configuration changes of NVM. So for example, if the NVM dynamic configuration parameter is set to false, then the NVRAM manager shall ignore the stored configuration ID. The compiled configuration ID that we stored in block ID 1 will be ignored at the startup time during NVM read all. So as a result, we'll not be any more checking what is the current configuration. Is it matching with the new software or something like that? No configuration checks are performed. We are just ignoring that. But what we do is, like in this case, we'll just check for its validity of the RAM block. Now, if the RAM block content is like detected as some invalid, in that case we'll go for the NV block. And if the NV block value is valid, we shall copy it to its assigned RAM block. If the value that is there in NV block is also detected to be faulty. In this case, we'll load the default data. So this is the case when NVM dynamic configuration is set to false. Now the other scenario is if we enable this configuration, that is dynamic configuration is set to true. Now this configuration ID check will be used. Okay, so the value that we are storing in block ID 1 will now be used, and a comparison will happen every time we start up. And as a result, we'll be able to compare and take action if there is some mismatch in configuration. So to take that action, the how the action is taken will depend on another configuration parameter, which is NVM resistant to change software. So let's try to understand what is done when this parameter is used. Resistant to change software. So change of NVRAM configuration, okay, this needs to be indicated to NVM first. And how do we indicate that? We indicate that by updating the NVM compiled config ID. So if in any project you update the configuration, then you, for example, you added few blocks extra or something like that, then in that case the configuration is changed, right? It's different from the previous configuration. So this needs to be updated, and this can be updated in this NVM compile config ID. So for this, we will be using a separate NVRAM block, which we discussed, and with the value or with the ID 1. So during every NVM read all, the module compares the stored value in NV memory with the value that is configured in NVM compile config ID. So once this read all operation happens, we will do this comparison. Now, if the value does not match, NV memory will be overwritten by the new ID in the next shutdown phase when NVM write roll is called. Okay, so once the software runs, if we see that the ID is different, we will update this ID during the shutdown phase when NVM write roll is performed. So after that next cycle, we will see that the configuration IDs are matching. Now let's check how the parameter will behave. See, if the configuration parameter NVM resistant to change software is set to true, RAM block will be initialized with data from NV memory even if a configuration change has occurred. Just before we spoke about what will be done in the NVM write roll, which is the shutdown phase. But what will be done at the startup phase will be depending on how this parameter is configured. So if this parameter is set to true, we will initialize the RAM block from NV memory, even if we detect that the configuration has changed. Now, if the parameter is disabled, that is set to false, we will ignore that. I mean, the NV block data is ignored because we can't take it anymore because the configurations are not matching. For example, if there is 6 blocks that are configured in the NV memory, maybe the current configuration has 8 blocks, and then there can be mismatch in the IDs. So in that case, we are preventing that to happen. So that's why we are not fetching the data from NV block. And instead, we'll use the default data, which is loaded. And it is loaded only if it is configured, right? I showed you 2 parameters. One is the address and one is the callback. If any of these are available, then we'll be loading the default data. So that's what is said here. Default data is configured via either the parameter, the NVM ROM block data address, or the NVM init block callback. So that's all about the NVM features. We have discussed a lot of features, and I highly request you to go through each and every one of them so that you become clear and you'll be able to easily apply them in your project depending upon the requirement.